buongiorno. It is quite a pleasure for me to be again in the countries that has produced scientists like Galileo and artists like Leonardo and maybe Brunelleschi del Montalcino, Brunello del Montalcino. And it's good to see old friends and make new friends. So,
mi permetto di fare un riassunto di quello che ha detto il professor Stefanescu all'inizio, che è molto contento di essere presente nel paese di Leonardo, chiaramente Leonardo da Vinci, nel paese del grande architetto Brunelleschi, e siccome è un grande estimatore dei vini anche nel paese di Brunello di Montalcino.
So I will try to talk to you about mold metal interface phenomenon in cast iron, and I will discuss. Just a second here. Right. The significance of surface quality, physics and chemistry of mold metal interaction, casting skin, and metal penetration in sand molds, and then expansion penetration, mechanical penetration, chemical penetration.
Molto spesso nell'ultimo tempo ci troviamo con un difetto nelle fonderie di Lisa diciamo terminologia americana, si chiama casting skin, però una traduzione, io ho provato a tradurre questa presentazione che probabilmente dopo la troverete sul sito Asofont, una traduzione troppo tecnica sarebbe la pere del getto, però il difetto è molto più complesso perché non dipende solo dalla estetica, perché la pere del getto potrebbe portarci con l'idea alla superficiale estetica del getto, però il fenomeno è molto più complesso perché tiene anche delle penetrazioni del metallo liquido e tiene anche, come vedremo dopo, anche della degenerazione dello strato superficiale. Il professor Stefanescu mi suggerisce di far vedere direttamente la presentazione in italiana e così perdiamo un po' meno tempo, visto che il tempo è quello che c'è, perdiamo un po' meno tempo con la traduzione. Un momento solo.
Qualche secondo per informarvi di cose a livello generale di cui non avevo ancora informato. Come vedete ci sono delle telecamere e tutti i lavori del congresso, sia di oggi che di domani, saranno completamente ripresi, anche perché le sessioni di oggi pomeriggio, essendo parallele, non avendo ubiquità, la gente non potrà seguire in contemporanea, per cui tutto il materiale ovviamente di questi giorni verrà reso disponibile sul sito dedicato e anche attraverso un supporto fisico di cui distribuiremo, per cui sia le presentazioni sia tutte le registrazioni audio e video, per cui sarà integralmente registrato e reso disponibile ai presenti e anche a chi non ha partecipato.
Okay, so we'll continue with the presentation in Italian and the talk in English, so we'll see how that works. So I'll talk about the significance of casting skin. I'll continue to call it in English. The physics and chemistry of the interaction between the metal and the mold in ferrous alloys only. And then about the casting skin, the strato superficiale done getto. And then penetration of the liquid metal into the mold, expansion penetration, mechanical penetration, and chemical penetration. So castings retain most of their casting skin in use. So the casting skin is very important. It's important, first of all, from the standpoint of aesthetics, but the casting skin affects mechanical properties very much, and in certain cases, even whether the casting is going to be rejected or not. And in a first approach, we can classify the defects as roughness, which is mostly an aesthetic issue, perlitic ring, which is a mild interaction between the mold and the metal, which typically decreases machinability. The occurrence of degenerated graphite, which improves machinability, which can improve or decrease machinability depending on whether we talk about ductile iron or gray iron. And then we can have severe interactions where we have penetration, mechanical penetration, which affects the aesthetics and can be corrected many times. And the mistake here, chemical penetration, penetrazione chemical. Chemical penetration, which can be also severe and requires rework of the surface. So the interaction between the mold and the metal interface can be first physical, and what I'm showing here, you have the molding sand and the metal. There is this metallostatic pressure that tends to push the metal into the mold, and this is opposed by the capillary pressure. And then we have chemical interaction. Now you have reaction between the elements in the mold, like oxygen and water and nitrogen, and the elements in the metal, which is of course iron, but also carbon, silicon, and all the others. And if it's a ductile iron or compacted, then magnesium and cerium. The interaction, the physical interaction, to keep up with my English. You can have a mild interaction, and you can see here I'm trying to show that the metal only does not penetrate beyond the first layer of sand. What opposes this penetration is the capillary pressure, which is a function of the surface energy of the metal and the grain size. And you can see the effect, it's roughness. Okay. Or you can have severe interaction. Now the metal is pushed beyond the first layer. As you can see here, the dark part is the sand, and the white part is a metal. You create a kind of metal composite here. You can see that the interface is very clear. There is no chemical reaction here. Okay. But that now requires really reworking of the iron. And then in the chemical interaction, we can have a mild interaction. Where you have subsurface damage. So it's light because there is no oxidation of iron yet. The cast iron has carbon in it, and carbon protects iron from oxidation. So first you have oxidation in the metal, of the carbon in the metal oxidized by oxygen of water. And so you have a decarburized zone, or you may have a perlitic rim. If you have magnesium, then you are going to have oxidation of magnesium too by carbon dioxide, water, oxygen. And now you are going to have a region that is poor in magnesium, and the structure here is compacted vermicular graphite, while here you have lamellar graphite, and here you have a relatively thin layer, but depending on the height of the same casting, you may have a very thick layer. And here are some other examples of decarburized layer, degenerated graphite in a spheroidal graphite casting. And the interaction can be severe, and it's severe when all the carbon has been oxidized in the superficial layer because of the water in the mold mostly. And then now, after oxidizing all the carbon, we start oxidizing the iron, producing iron oxide, and eventually iron oxide combines with silicon dioxide, which is your sand, to form fayalite. The melting point of fayalite is about 1100, so it is lower than the melting point of iron. So you may have solid iron, but you have still liquid fayalite. And now you see a very ugly region here, where you have oxidized, that's for steel, oxidized steel. If you look at higher magnification, you have your silica grain, and you have the steel here, you have iron oxide, and in between you have fayalite. And that will continue to penetrate even after the steel is solid. So I will talk first about the casting skin. And here is an example of casting skin. What's composing the casting skin? It's the surface roughness, perlitic border, graphite degradation. You can see it here, graphite degradation. Graphite depletion. So in some instances, that's not the case. You have no graphite at all. And then a region where the nodularity has been altered. And this is an example from a casting. Here is a core. Here is a casting. Okay. So you can see here that depending on the height in the mold, so these are 4 different micrographs at 4 different heights. For the same material and same molding materials, you can have quite a change, a significant change into the thickness of the skin. And we're looking at some of the effects of the skin on static mechanical properties. You see that as the skin thickness increases, the tensile strength goes down significantly, and the elongation goes down. This is a compacted graphite. No, it's not Giza spheroidale, it's vermicular. And here it's an effect of the surface condition, because we have means to deal with the surface condition. For example, this is the properties if I take the sample without machining as cast, and if you machine the sample, then the strength goes up significantly. And then if you shot blast the sample without machining, so this is as cast and then shot blast, and you can see a much higher increase in strength. And this is when you shot blast it for a longer time. So I think this was 2 minutes and this was 5 minutes. And the effect of shot blasting is basically to decrease the casting thickness from 0.183 millimeters to 0.125, and then after 5 minutes completely remove it. And so we defined, we always want to put numbers and quantify any effect. We defined what we call a casting skin factor, which is simply the ratio between the tensile strength of the as cast sample and the tensile strength of the machine sample. So it's always smaller than 1. When it's 1, that means we have no effect. And to give you 2 examples, for spheroidal graphite cast iron, this casting skin for our experiments was 0.93, and for compacted graphite cast iron, it was much larger, 0.84, and I'll explain why. So compacted graphite cast iron is affected more by the mold than it is ductile. And here is the effect on fatigue resistance. The red points are as cast. These points are machined, and you can see that the sample that is as cast has much lower fatigue strength at the end, and that is because of this casting skin. And you can define in the same way a casting a skin factor for fatigue. Same thing, ratio between as cast and machine, and you can see that it is affected by nodularity, and it's much lower than when the nodularity is less. And here are some examples of the effect of shot blasting. You can see how the surface is affected by shot blasting. You see a lot of deformation, plastic deformation. And here is a comparison, as cast and shot blasted, machined, and machine and shot blasted. And you see, once you shot blast and machine, there is not much difference. And the effect of the sand, sodium silicate and furan sand, you are going to find different effects depending on the sand. And so, some of the experiments were, I already told you that you can decrease the effect of casting skin by shot blasting, but in the regions where you have pore, of course you cannot shot blast, so you have to address the problem in a different way, and that different way is to use molding coatings, mold coatings, and we classify them as inactive, active, and reactive. Okay, inactive means there is absolutely no reaction, there is just a barrier. Active, they will alter the composition of the metal in the layer, and reactive, they have a reaction, like when you add magnesium, then you have reaction with the metal. And I'll give you some examples. I can't spend a lot of time, but you can see here it's an iron, different carbon equivalent, 4.1, 4.3, 4.5, and the effect, no coating, ferrosilicon, and graphite. And these effects are summarized in this graph. You see, if you add graphite, it's not very good. So first of all, no coating is this line here, no coating. So if you see, if we add graphite, it's very good for low carbon equivalent iron, but not for high carbon equivalent iron, not much change. But for high carbon equivalent iron, ferrosilicon works very well. So depending on the kind of iron, you may have to use different coatings. And here is an example of reactive coatings. Like this is a no coating, and this is when you add ferrosilicon magnesium. So actually you are adding a little bit of magnesium on the surface. So this ferrosilicon magnesium is mixed in the coating, and now you have a little bit of magnesium going back into your melt. Magnesium oxide doesn't have any effect. Calcium oxide has some effect, but ferrosilicon magnesium much better effect. And here is kind of a summary when you have a lot of different coatings, and I'm afraid I don't have time to explain all of that. This will be published on the internet, and you'll have access to this, and you can look at all the details. So I try to put more than I can cover, so you can take it home and get more out of it. So this is a summary of all the mold coatings on skin thickness, and this is for 3 different carbon equivalent: low, medium, and high. And you can see first of all that as you increase the carbon equivalent, you decrease the casting skin. And then the most efficient for high carbon equivalent is ferrosilicon. And you can see that the zirconia is not very effective. And when you have a resin, so this is for silicate bonded mold, you have very different effect depending on the mold. And this is for the furanic resin bonded mold. And you can see here the most efficient is ferrosilicon magnesium. You have sulfur in the resin bonded mold, so you have to counteract the sulfur. You don't have sulfur in the sodium silicate, mostly oxygen is the reason. And of course, as faculty, scientists, we spend a lot of time trying to understand. So I have another talk, 40 slides, just on the mechanism. What really happens, and how do you counteract it? And I cannot cover this in this time that I have. But if you read down, I'll give you a minute to read it because it probably explains it better than I could do it in English. Okay. So in summary, in the molding sand you have oxygen, you have sulfur, and you have some carbon. In the adjacent liquid you have carbon, magnesium, and cerium. And the sulfur and the oxygen will react with the magnesium in the layer at the interface and will result in degeneration of graphite. Oxygen will oxidize the carbon and it will remove graphite. And it will also remove the nuclei for the solid transformation, and therefore will form a perlytic board. And the carbon may result in increasing the carbon content in the superficial layer and give you a perlytic board. Alright, so now I'm going to talk about metal penetration. Okay. So there are a number of basic mechanisms. We can have mechanical penetration, we can have chemical penetration, vapor state penetration, explosion penetration, but 95% of all penetration defects in castings are accounted by mechanical and chemical penetration. So I'm going to spend most of my time talking about this too. So here is a sequence of penetration. As you start with some liquid metal, you have metallostatic pressure that is affecting all the way until during solidification and result in degeneration of the superficial layer. You have dynamic penetration that is only as you fill the mold. After that, the metal gets quiet and dynamic penetration doesn't occur. And then you have expansion penetration that occurs during eutectic solidification only for cast iron. And that goes all the way to the end of solidification. And here is an example of the way we understand explosion penetration. You can see it here. That's a case of explosion penetration. So what happens, for example, in this casting, as solidification proceeds and you have graphite expansion, the metal is pushed out to the riser. But if you have a hot spot here, you are going to still have liquid metal here at the corner. And then if the riser has been closed and you still have expansion, the metal is pushed in the mold. So that's expansion penetration. So the solution to that is the way you design your mold and gating system. In mechanical penetration, we understand this by simply a force balance. So if you look at what's trying to push the metal in, static pressure, dynamic pressure, expansion pressure. And what prevents it from going in is the capillary pressure, the most important, the friction pressure, and if you have gases from the mold, the gases coming in. And we can simplify the equation and then simply solve it as an equation between the balance between the static and dynamic pressure and the capillary and friction pressure. And I'm going to show you this equation, and that's probably the only equation. But what's interesting in this equation calculates the length of penetration, how much the metal penetrates in the mold. And you can see the variables. Here are all variables that you can relate to the foundry. So it's GFN, the diameter of the grain, the pouring time, the fraction of grains, which is bulk density of hardness of your mold, the viscosity of your liquid metal, density of the metal, metallostatic pressure, height of the mold, velocity of the metal coming into the mold, and again the grain density, the grain size. So these are all, we translated all these physical parameters in parameters that you measure in the foundry. And of course you are not interested in knowing how much the metal penetrates, you want it not to penetrate. So you take this equation and if you plot it, for example, against this contact angle, you find out that above a certain angle there is zero penetration. And so there is a critical angle. And so all we need to find is what's this critical angle? What does it need to be so I can always be above and have no penetration? And this critical angle depends, in this case, on the height, in this case on the diameter of the grain, so it depends on all of these variables. So we define this critical angle, and now we have to introduce all our foundry variables here. And we have the penetration index, which is a ratio between the critical angle and the actual contact angle. And the actual contact angle is the contact angle of your metal, which is a function of composition, and it's a function of temperature. And so if this index is higher than 1, you have penetration, no penetration. If it's in between 0 and 1, you have mechanical penetration. It is smaller than 1, then you have chemical penetration. And it was about 5 years of work on this project. We had about 20 foundries working with us, because now we had to each of these parameters had to be measured experimentally, and then get statistical equations, and then put into a program that eventually ended up in the foundry. And 5 minutes, okay, so I'm running short of time. Here is an example of how do you measure this contact angle. You can see we start with a cube, and then it's sitting on quartz, and then you can see it's not wetting here. And here is when you put iron oxide on quartz, you can see it's wetting, and you can see it's very bad. We ended up with a software that we gave to the foundries, and they simply introduced their variables here. Okay, the composition of your iron, GFN, NQI, metallostatic head, and metal velocity. And then it calculates directly this penetration index. Okay, I'm going to skip that. I want to talk a little bit about chemical penetration. So here what happens, as we discussed, you have carbon that is oxidized by water vapors in the mold, iron that is oxidized in the formation of phyllite. And here is a simple example. So this time the substrate here is sand. Okay, and this is an iron oxide, and we start melting it, and what we see is simply disappearing. So what it does, it sinks into the sand. You have phyllite here, and the phyllite goes in, and at the end, this is what's left. So that's an example of how this penetration works. Okay, and this is something I talked a little bit at the beginning. We have all these reactions that occur between elements in the metal, elements in the sand, and elements, the gas in the sand mold, and you get very nasty looking microstructure where your steel is here, and you have sand here, but then you have iron oxide and phyllite, and that's a very bad issue. And so we did it in the same way. We established a penetration index, which in this case, I will explain it here, and that's probably close to conclusion now. If you have the mold here, you have oxygen coming from the mold to the surface. You have carbon coming from the surface to the mold because carbon here is oxidized, so you have a carbon gradient. And then you have a critical carbon. And if the carbon in the metal goes lower than this critical carbon, then you have iron oxidation. So all these parameters must have been defined mathematically. The critical carbon, the diffusion, that was a simple one. Complicated was the critical carbon. No, these two were simple. The complicated was to get a model to show how much oxygen is coming from the mold, because molds are so different. And here is an example of the results, and one more slide after that. If you have 0.2 carbon in steel, the actual carbon is always smaller than the critical carbon, so you always have penetration. But if you start adding carbon, now you have a region where you may not have penetration, but you are going to have penetration later as the time is longer, more carbon oxidation, more penetration. So how do we solve this problem? For steel, for example, we add carbonaceous materials in the mold that will have carbon that is oxidized by the mold, so we don't oxidize the steel. And we experimented with oxidizing atmosphere, and that increased the probabilities of penetration. And if we have higher carbon in steel, that also decreases the probability of penetration. Mille grazie.
Ringrazio il professore e invito, se qualcuno avesse delle domande, a approfittare della selezione e a porle. Da parte mia mi sembra interessante vedere come certi lavori di ricerca possono avere un contenuto pratico, concreto, molto forte, perché tutti, credo, la nostra attività li abbiamo affrontati, e aggiungo una considerazione veloce sul fatto che, come ho detto forse prima, ma uno degli sviluppi importanti del nostro mercato è alleggerire, assottigliare le superfici, e questo dipenderà molto di più dalla capacità di migliorare i sistemi di formatura che non tanto dalla metallurgia, che è già abbastanza vicina a questi risultati. Ringraziamo il professore che sarà comunque a disposizione per